We're on.
Hey everybody, welcome back.
We're back.
We're back. We're back here today, and we're talking today about sine waves and frequency. Yeah.
Yep.
So it'll be a fun time. Just want to kind of give you like the overview of how AC is functionally a little different than DC.
Yep.
So.
All right. Well, let's get to it.
Let's hit it. So with DC, we have current flowing in one direction. Pretty simple. Electrons flow from the negative terminal to the positive terminal through whatever we've got on that circuit.
Something we saw in IMO quite a bit. We played with the trainers that we had. We're doing our voltage checks.
Yeah.
And
we have that set to voltage DC. If we hook a voltmeter up to it, we read a number.
Yep.
And that's what that is. Now, let's imagine what would happen if we were switching from current flowing in one direction to switching it from going back and forth and back and forth. So kind of just think about, what does this power supply look like? If we connect a voltmeter to that, what does that read? So let's kind of examine what it looks like, and then we'll talk about how the voltmeter reads it. So what does this look like? Here's an animation that kind of gives you the idea of what's going on here. In DC, it's a constant march in one direction, and then if we look at our AC flow over there, that AC flow is just going one way and then back the other way. And you can see just one electron in this picture, if you picture those as electrons, just moving a little bit in one direction and then moving back in the other direction, moving a little bit in one direction, moving back in the other direction. So keep that in mind as we start looking at a way in which we can switch that back and forth. And that would be simply through a switch. So if we hit the next slide.
And by the way, these animations are a lot slower than...
Obviously, electrons move close to the speed of light. Yeah. So keep that in mind. So we've got a simple circuit here. Our simple circuit here is just has essentially two connections that we can hook up our power supply to. If we hook it up in one direction, we get current flowing in one way. If we hook it up in the other direction, we've got current flowing in the opposite direction. So you can cross those over. So if we graph this circuit, what's it going to look like if we're switching back and forth and back and forth? So up at the top of the tree, we've got our current state of the system. And that current state of the system is an open circuit.
No current flowing.
So there's no current flowing. If we look at that graph down there on the bottom, the green line just represents a constant no voltage.
Yep.
If we hook it up, we get a positive voltage. And so you see that graph showing that it's switched to going positive there.
If we flip that around though,
it all of a sudden zips down and it becomes a negative. And so as a result, we have it goes straight down and become the bottom. Now, when we get this, we've got part of a wave form here. So it moves to the other side of the zero line. And this would be a very simple waveform of alternating current. It's called a square wave. In most circuits, we don't have that. It's pretty, in most circuits, it's more of a gradual decay and a gradual rise of that current.
But the square wave does exist. We do see it in digital circuits.
Anytime we're actually just switching.
Yeah, switching.
Back and forth, a signal that is DC, we can achieve the square wave. And so you'll see that used a lot of times when we're doing that with DC. Mm-hmm. AC, on the other hand, is a more smooth transition. And we get a sine wave out of that.
Something I think we talked about earlier is kind of with music, right?
Mm-hmm.
Digital version versus actual,
like an analog recording of it. You get all of the things. If you talk about like auto-tune, you can hear that sort of choppiness. Yeah, the choppiness of it.
Think of that as a square wave.
It's that square wave, as opposed to what would naturally be more of a sine wave. So let's talk about the sine wave. Just how the components of how that looks. We have voltage up there on a y-axis, and time is on the x-axis here. So when we're talking about a sine wave, we can break that down into a cycle. And a cycle is essentially when it goes and maxes out in the positive, and then maxes out in the minimum, in the negative, and then returns back to zero.
Yeah. So if you were to overlay these, if you take the negative end on that and flip that back towards on itself, it would basically be a loop.
Yeah.
And once that full cycle is completed, essentially when you lay it out in this time format, you see that it reaches that zero line at the end of it.
So your cycle is essentially going around in a loop. It's going from zero to positive, it's going back to zero, and then it's going negative, and then it's going back to zero. That equals one cycle. A period is what we measure on that x-axis. And so that's time, the time that it takes to go through one cycle. And that would be measured in seconds.
Pretty simple. And what is frequency?
So frequency is when we say how many cycles happen in 1 second. So for instance, in this graph here, we have 1 second, and we can see that we have 4 distinct cycles that happen within that 1 second. So what about period? Well, the period of this is actually just the inverse of that, 1/4 of a second. There's 4 cycles per second. Each cycle takes 1/4 of a second. So quite simply, next slide, we'll give it away.
Yep, there you go.
Frequency is the inverse, or period is the inverse of frequency. So take what we get coming out of the wall, because that's what we've got coming out of each of the plugs, each of the outlets in our house.
We hear it a lot, 60 hertz. Right?
We hear it a lot, 60 hertz. 60 hertz.
What is a hertz?
A hertz is what cycles per second is. That's just a shorter way of saying cycles per second.
Yeah.
So it's much easier to just say hertz.
Yeah.
So our frequency is going to be 60 hertz or 60 cycles per second. And that means that the period of what comes out of the wall is going to be going through and doing one cycle every 1/60th of a second. Now we're going to analyze the sine wave much further later on. We're going to dice it up. We're going to deal with phase angles. We're going to do all of these things. Those are topics for a later video. But first, let's kind of look at how we generate AC and the relation between that and the sine wave. So go ahead here.
All right. AC generator.
Here's an AC generator. This is a 3-phase generator. Don't let it confuse you. 3-phase generators are used to create essentially 3 individual phases, 3 individual circuits. Each one is offset from the other through the geometry of the generator.
So why 3-phase and not 1-phase?
Well, if we did 1 phase, if you would look at that, we would only have, like, say, the coils that are A in there. We wouldn't have B and C. It wouldn't be a really good usage of space. There's some other reasons that we'll get into later when we start talking about motors and drives, why 3-phase is good for power. But you can't use necessarily all 3 phases except in certain types of motors. So it's basically for when you do the reverse of the generation that you can make use of those phases. In fact, in our homes, most of the time we only have 2 phases that are coming into our homes. And we only use one of those at a time. Right. At your breaker box, it's splitting those off, and you're only getting one of the phases to each outlet. So you have the phase, like the hot wire and the neutral.
Right.
So that's one single phase.
So you think these would be better applications, at least for 3-phase, for industrial use?
For industrial use, it's really good for motors because they are able to produce more consistent torque, because whenever one of the phases is passing through zero, another one is reaching its peak and another one that's reaching its minimum. So it's a really good thing that you can use these for that makes motors a lot more efficient.
More efficient, more consistent power delivery, right?
Consistent torque delivery, all of those things. But when you're generating it, it just makes sense for the space of it to not generate just a single phase. You might as well generate 3 phases.
So that just means they're more expensive, huh?
Yeah. I mean, yeah. So there you go. Let's plow on to the next slide. So this is the relationship between that and what we're talking about when we're talking about sine, right? We talk about trigonometry. So if we look at this sine, and if we look at the angle there, this represents essentially what's happening inside that generator. You've got a rotating member, and how far away it is from that magnet is determined by this rotary motion, and that is a function of sine. And you can use cosine, but it references a different axis. So just kind of look at this and relate that to what you see inside our generator model. And that's how you can understand, okay, that's how sine relates to what I saw on that AC generator. So for every cycle rotation, every time it goes around, it's going, depending on whether it's the north or south pole that's close to the coil, you've got a cycle completed. Because if it goes all the way around one whole rotation, each of those field windings is hitting the north pole, and each of them is hitting the south pole once, and that means that we're going to have positive and negative associated with it. So that means that one cycle is one rotation. Yep. And if our generator spins at one rotation, RPM is a typo here, but if one rotation per second, we would get a frequency of 1 hertz because we contain one cycle. That means that if we have a generator spinning 60 times per second,
that's where we're getting our 60 hertz from.
That's where we're getting our 60 hertz from. Now, 60 times per second is actually 360 RPMs, because we have to add 60 seconds in a minute to get RPMs. There's all kinds of things that are in the motors stuff that you're learning in other videos. So poles, stators, commutators, things like that. Those will all be covered in further detail in those motor videos.
Stay tuned.
Stay tuned. You may have already watched them at this point.
I think we covered this.
Yeah, all of this boils down to this. This is just kind of a summation here. The sine wave is a function of the position of a coil in a magnetic field. So there you go. So then, why do we use AC? It seems a little bit more complex.
Yeah, I mean, obviously we talked about industrial use, which is huge. I mean, without AC power, a lot of that.
And once you get into the mechanics of motors and why AC motors make a lot of sense, you'll kind of understand that.
Yeah, you could probably look up some of the voltage wars as why we use AC versus DC.
There's a whole lot that goes on with between Edison and Tesla back in the day. Edison went and fried an elephant. That's
interesting history. It's
the interesting history of it, but it was always going to be the way that it is, right? DC makes sense only when you're generating it locally. If you've got a solar system, DC is the way to go. Most of the things, you could get things to do that, and if anything that you need AC for, you could get an inverter for, if you're generating your electricity at your home.
Long distance, though, you're going to need
long distance. You need AC, and that's a whole number of reasons that we will kind of glance at here, but we'll definitely dive further into when we have a video on power supplies and transformers.
Yeah, a lot cheaper to get AC out to everybody than it is DC. DC, you would need a lot more infrastructure, a lot more substations, etc. There's a
lot of stuff that goes into that. You'll like in future videos we'll explore the exact reasons why, but the main like thrust of it is AC can utilize something called transformers. And transformers are a way for us to change the voltage of AC. All right, let's go to the next slide here. In DC, how do we change the voltage?
Well, we use rectifiers. You mean from AC to DC?
No, how do like if we have DC, if we have 24 volt DC and we need 12.
Oh, well then we just add a resistor.
Yeah, we create a voltage divider using a resistor. What happens? Yeah, we create a voltage drop. What happens to the energy on that voltage?
Oh, dissipated as heat, typically.
Yeah. Like that resistor is using up energy. It's dissipating as heat. Well, that's not very efficient.
No, unless you want to.
Unless you like paying a lot of money for your electricity, that's on you, but like we strive for efficiency. We want to generate good, we want to generate electricity and we don't want to waste it. So it's much easier, more efficient with AC to change voltages. Because we get zero loss when we change voltages with AC. And we'll get into that when we start talking about the particulars of transformers in our power supply video. But you just need to know that. And then the other aspect of this, and that also has to do with transformers, and we'll get explained more, is that it's much easier to transmit, as we've said before. So that's kind of our introductory video. You'll see more when we start talking about power supplies and when we talk about electromagnetism. You'll see more about what's going on in these systems around AC that will make it really apparent why we use it. So that's all for this video. We'll see you in the next one.
Thank you guys for joining.